Now we're going to have a look at the convergence of alternating sequences. So these are sequences which alternate between positive and negative terms, and we've seen a few, and the formula for an is usually minus 1 to the n times some positive term an prime, or minus 1 to the n plus 1 times an prime, where an prime is a formula for a positive number. So it's quite often simple enough to determine whether these alternating sequences converge or not. Because they bounce back and forth between positive and negative numbers, the only way that such a sequence can converge is if the limit as n goes to infinity of the absolute value of the terms is 0, or the limit as n goes to infinity of the positive part, an prime, approaches 0. Of course, this is because if it approaches anything else, as we'll see in a diagram later, the terms of the sequence bounce back and forth between positive and negative numbers that are far away from each other. This is quite often a simple test to apply, and we're going to apply it here to two sequences. So let's look at the sequence A here and try to figure out whether it converges or diverges. But certainly an alternating sequence, its nth term is given by minus 1 to the n times 2n plus 1 over n squared, and of course the positive part there is 2n plus 1 over n squared. This converges only if the limit as n goes to infinity of the absolute value is 0. And the absolute value is what you get when you ignore the minus 1 to the n part. So we need to calculate the limit as n goes to infinity of 2n plus 1 over n squared. Now if I replace that n by an x, I get a nice rational function for which I can calculate the limit using the techniques from Calc 1. It's the limit as x approaches infinity of 2x plus 1 over x squared. And remember, I should divide the numerator and denominator by the highest power of x in the denominator, which is x squared here. So when I do that, it's equal to the limit as x approaches infinity of 2 over x plus 1 over x squared divided by 1, and that limit is obviously 0. So that's actually enough to conclude that this alternating sequence converges, and we can actually say it converges to 0. Let's check the sequence B. Here Bn is minus 1 to the n over 2n plus 1 over n. It's a similar looking sequence, but we'll see that this actually diverges. The theorem says that this converges if and only if the limit as n goes to infinity of the absolute values is 0. And the limit as n goes to infinity of the absolute value of Bn is the limit as n approaches infinity of 2n plus 1 over n. We can just disregard the minus 1 to the n here. I can replace the n by an x as before, and I get the limit as x approaches infinity of 2x plus 1 over x. And dividing above and below by x, I'm looking at the limit as x approaches infinity of 2 plus 1 over x. And this is 2, which is obviously not 0, and therefore the theorem says that this sequence diverges. Well, you can see geometrically what's going on here. I've drawn pictures, graphs of both sequences. On the left, the terms are alternating, they're bouncing back and forth. Remember, the y values in this graph is the actual value of the sequence for the given n, which appears on the x-axis. So the y values bounce back and forth above and below our x-axis or our n-axis, but because the absolute value goes to 0, they tend towards the single horizontal asymptote y equals 0. On the other hand, for sequence B, the y values bounce back and forth, and instead of tending towards a single value, the negative ones approach minus 2 as n approaches infinity, and the positive ones approach plus 2 as n approaches infinity.